during the meeting. The one this afternoon is on DCMB and perspectives to be given by Jim Peebles. Please, Jim, take the floor.
This is this one? It doesn't matter. Good. Colleagues, it's a real pleasure to join you on this special occasion. I propose to offer a few comments about how cosmology got to its present state, and then present a few observations about the present state of this subject. You can find a lot more of the story of how the CI cosmic microwave background contributed to the development of cosmology in this book, Finding the Big Bang, by Lyman Page, Bruce Partridge, and me. We're all three here. It's a great read. I draw from Hubble's Realm of the Nebulae, published in 1936, the state of cosmology in 1936 when I was 1 year old. People then had Einstein's general relativity theory. They had the persuasive notion that a philosophically attractive universe would be homogeneous. They recognized that an expanding homogeneous universe would have redshift directly proportional to distance, suitably defined. And they had quite a spectacular observational test of this linear relation. Here the discovery plot, different scale, you'll discount that, but notice that a spectacular continuation by Hubble and Hubbleson reaching redshift 10% of the velocity of light. Really impressive. The distribution of galaxies was not well characterized. Hubble did make deep galaxy counts, and he reached, again, roughly a redshift of 0.1. His counts indicated a slightly slower increase with limiting apparent magnitude than you would expect in a homogeneous universe. We're now inclined to think that that's a result of systematic error in his magnitude scale. One could, at the time, ask whether that meant that the homogeneity assumption failed. On the other hand, the linearity of the redshift-distance relation certainly argued for a homogeneous universe. We get some feeling for the nature of cosmology then and now through the 1950s by imagining an alternative universe in which all is the same as in our world, except that Hubble and Hubbleson were able to extend the redshift magnitude relation by another factor of 10 in distance using supernovae, and that they saw the curvature. Let us ask ourselves now how this situation would have been assessed in 1950, let us say, when we had the steady state cosmology in competition to the Big Bang. Recall that in the steady state theory, continuously created matter pools to form young galaxies to replace the old galaxies that are moving apart. If space-time is described by a metric theory in the steady state universe, then the metric has to be de Sitter with exponential expansion. The redshift magnitude relation is predicted with no free parameters. We can then imagine a dialogue, which I have attempted to frame in the style of debate I used to hear in the old days. So steady state, we predicted that. Big Bang, we can fit it too, just to throw in a lambda. Steady state, you're just playing with parameters. And have you paused to consider that you have based your considerations on general relativity theory? At this time, general relativity theory is seriously tested by just one measurement, precession of the perihelion of Mercury. Redshift, bending of light, they were both at best marginally detected. You are taking this theory, tested on the scale of 10 to the 13 centimeters, let us say, you're extrapolating it to the Hubble length, about 14 orders of magnitude in length scale. Why would anybody pay any attention to such a spectacular extrapolation of such a schematically tested theory? A question that we should be asking ourselves still. The rejoinder, at least we have a theory. And have you paused to consider that in our theory, those supernovae you observed at redshift 1 are living in a systematically different universe. They must be different from present-day supernovae at some level. I deeply respect the care with which the observers have looked for this systematic difference and put limits on it, but they can't have covered all possibilities. How easy to imagine that they've missed something. that in fact the curvature is not there, destroying your steady state success, and that we don't need that ugly lambda. It's a de Sitter universe. Well, it's clear from this debate that we need more data. Of course, the CMB was a big factor in that. I remind you that in a series of paper leading up to 1948, George Gamow developed the hot Big Bang theory. It was a stroke of genius. He presented the theory for the origin of deuterium and helium. That, with elaborations, is our present well-tested theory. In the same way, and 2 years earlier, Bob Dicke, in a burst of genius, first invented the microwave Dicke radiometer, used it to present a bound on the temperature of extraterrestrial radiation, less than 20 degrees, where you remember that Gamow's theory would present a present temperature, well, quite uncertain because they didn't know the present baryon density, but somewhere around 5 degrees. And in another burst of genius, Bob Dicke, 15 years later, persuaded two of his young associates, Dave Wilkinson and Peter Roll, to build a Dicke radiometer to look for this radiation. The radiation was in fact discovered in communications experiments by Bell telephone engineers. Here you see an accounting of the noise in their system. They had, why do I keep pressing the wrong button? Very low noise traveling wave maser amplifier, careful accounting of all of the noise budget, and an excess which they ascribed to backlobe pickup. These engineers knew full well that this horn reflector antenna is much better than that. They had to put the noise somewhere. 5 years later, Penzias and Wilson had convinced themselves that they could not find the source of this excess noise. It was news of the Roll-Wilkinson experiment that led them to realize that they had found possibly what Roll and Wilkinson were looking for. Here was a situation a year later. Luckily, Princeton was working at a different wavelength from Bell Labs. John Shakeshaft came in quickly with another measurement, and we had the CN interstellar cyanogen spin temperature, which some astronomers had known for years is surprisingly high. This is the spin temperature obtained by getting the ratio of populations in the ground level and a rotationally excited level of interstellar cyanogen through absorption lines. The surprisingly high spin temperature is hard to understand because the rate of decay of the excited cyanogen is quite short, quite fast, and it's hard to see how collisions with particles can have excited the rotation. It fits pretty well with a thermal spectrum. We get some feeling for how this was greeted by steady state people from this discussion by Fred Hoyle a couple of years after that, 1968. Hoyle pointed out that one could estimate energy densities in several forms, including the energy density in the microwave background, and that these energy densities are all quite similar. We see his comment, according to conventional views, the similarity is accidental. I pass over the next sentence. I simply cannot accept so many coincidences. There may be one accident, one criminal in the list, but it is likely that there's more than one. The criminal could, of course, be the microwave background, which could be a fossil from a hot Big Bang, but I do not think we are driven to this view with any real force. I would have said there was some force. After all, the spectrum did look pretty good, but it didn't, by no means could one assert with confidence that this is thermal radiation left over from a hot Big Bang. It was two groups who solved that problem. One, the Cosmic Background Explorer Working Group. It garnered 2 Nobel Prizes to John Mather, George Smoot. David Wilkinson, the leader behind all of this. The leader also, with Lyman Page, Norm Jurosik, and others, of the Microwave Anisotropy Probe satellite, later renamed the Wilkinson Microwave Anisotropy Probe, WMAP, in recognition of Dave's great contributions. A second group in close competition, Herb Gush from the University of British Columbia in Western Canada, and 2 able assistants, Mark Halper and Ed Wishnow. I confess to you now that because these people have done something great and I can't touch them. I can reveal to you that whenever I look at this photograph, I feel good. And I ask myself, if I didn't know these people had done something truly great, if this image was all I had to judge them by, would it have inspired confidence? Here are the results. It is moving to me to consider that these very similar results, either one of which would have settled the question, were obtained within 2 months of each other after almost 15 years of development in each case. Spectacular. Here is the present situation from Al Kogut, collected data. The dotted line, the theory, a thermal spectrum. The solid line, a measurement at the peak better than a part in 10 to the fourth. Spectacular. It has to be thermal radiation. The universe as it is now is optically thin. We can see distant radio sources at these wavelengths. The universe had to have passed through a phase when it was dense and hot enough to have been able to relax to thermal equilibrium. Evidence as tangible as dinosaur bones that said these remarkable creatures roamed the face of the earth. This is, in my book, an iconic image to be placed on the list of discoveries of which you may say, this changes everything. The universe is evolving. I might pause to remark that I have been careful, I hope, not to say the words Planck, black body spectrum, because the true situation is that the CMB is compared to thermal sources. It is not compared to the theoretical Planck function. I am told that the last test of the Planck function against standards of mass, energy, frequency was in the 1920s. They know how to do much better now, Kogut and colleagues. If you agree with me that neatness requires that we close this circle by checking the Planck spectrum, even though we don't expect any anomaly, demands that funding agencies face up to the obligation of allowing these people to make a precision test of the Planck spectrum. Well, after that brief commercial interruption, I come to the point, I should have remembered to say it well here. This is an iconic image of a great advance, but is by far complete. It requires local physics, it requires a metric theory of space-time, and that's about it. The universe must not have been so violent as to seriously disturb this energy. It mustn't have expanded so rapidly as to broker adiabaticity, and that's it. Tells us a lot, but not nearly as much as we learn from this network of cosmological tests. You have seen many of these figures today. You'll be seeing more tomorrow. I present it all as a, and I was very impressed by the care with which people, George Estadiou and others, worried about 2.5 sigma anomalies. They're right to do that, but from my point of view, I want the gold standard, 5 sigma. And so far as I've been able to hear, there are no 5 sigma anomalies in all these measurements. Now, I draw your attention to the fact that these measurements look at the universe from many sides. Consider the key project. Measure distances to galaxies, divide by the recession velocities, get a characteristic time, which beautifully blends in with these CMB measurements to give us a flat universe. Consider stellar evolution ages. In case you're not aware of it, astronomers, in order to confuse us, physicists plot surface temperatures of stars increasing to the left and luminosities increasing up, but numbers increasing down. For this star cluster, the evidence is that the stars have almost all the same age. The one parameter distinguishing them is their mass. Higher masses evolve more rapidly and move about in this Hertzsprung-Russell diagram. Fit the diagram to stellar evolution models, you get a time scale, which better not be bigger than the expansion time of the universe. And it must not be a lot less, because the evidence is that these stars formed early. In fact, it's not a precision test. What? You'd give this perhaps 20%. But it is looking at the universe in a quite different way and getting the same answer. I could go through all of these, but I think I won't. It gets tedious and academic. Let us just stress the point. Each of these measurements, I assert, is subject to systematic error. I don't care how precise you are, it's the nature of measurements. Each of these measurements is subject to systematic error in the form of analysis by the wrong theory. Any one of these measurements, I think, could be found to have been bungled, to have misled us totally. But it is quite inconceivable that these many different ways of looking at the universe so consistently point us in the same direction. You perhaps will have recalled that I am echoing Fred Hoyle's words. I have adjusted it slightly. His comment may refer to the thought that to a skeptic questioning conventional views, or it may be a supporter of conventional views questioning a skeptic. Either way, I cannot accept the many coincidences required to discount this evidence. This, I believe, is a firm statement of the way we do natural science. Let me remind you that physical science is a social construction. Who else? As a social construction, it came with no guarantee of success, though it has been spectacularly productive. It comes with no guarantee of uniqueness. We cannot prove that there is not some alternative physics that is also productive. We can only point out how ridiculously unlikely it is. But that, of course, is a societal judgment. And I guess I should finally say, we have not been issued guidelines on when to add new physics to the canon. Instead, we make the judgment ad hoc, adjusting the rules to fit the situation. And those adjustments can lead us to wild aberrations, the madness of crowds. This is, after all, a social operation. I give you the example of de Sitter universes. Everyone knew in the 80s that, well, at least a large fraction of the community, that lambda is 0, space curvature is 0. We live in an Einstein de Sitter universe. It's a universe we all would have chosen if we were consulted. We also notice that these errors and aberrations tend to correct and bring us to this very convincing story. So, it's here again. I come now to another question. If you agree with me that lambda CDM has been very convincingly tested and shown to be a good approximation to what actually happened as the universe expanded and cooled from redshifts 10 to the 10th, do we expect that lambda CDM is the final cosmology for the purposes of doing astronomy and cosmology at redshifts less than 10 to the 10th? Or do we imagine that it is just the simplest approximation we can get away with at the present level of accuracy of the tests? I confess that my response is, this can't be the end. And I guess I can rationalize that a little more by pointing out that the dark sector is modeled in a pathetically simple way. Surely there's more in there than the lambda CDM model. There is, I think many do agree with me on this, and there is a lot of talk of a lot of searches for new modified gravity, for more interesting physics in the dark sector. That may lead us to a still better cosmology than lambda CDM. Another possibility, of course, is to go after the phenomenology and ask yourself, can you find anomalies that are not, with reasonable plausibility, explainable by systematic errors or by statistical fluctuations? Chris Gorski mentioned one line of research on large scales. I have been very taken with the point that galaxies have a very rich phenomenology. They offer a new scale for probing the physics of cosmology, and we might ask ourselves, can we find in galaxy physics anomalies, clues that might lead us to a still better cosmology? Lambda CDM is rightly celebrated for its promise as a basis for a galaxy formation theory, and indeed it has had some remarkably impressive successes. Upper left, the galaxy stellar mass function. estimate the mass in each galaxy. Here is the probability distribution in galaxy masses. The data measurements are the symbols, the solid curves, the lambda CDM model fitted to these data. Now, because we do not understand how stars form, and we do not understand how star formation and evolution and death affects the baryons that are not in stars, we have to, in this game, invent parameters to describe what we do not know. There are here some 8 parameters. We're not, therefore, terribly surprised that it's a good fit. But we should be impressed that these same parameters will also fit the scatter plot, circular velocity at maximum around a galaxy model or measured against luminosity, the Tuller-Fisher Faber-Jackson relation, data points, model points, again, a pretty good fit. We may conclude, I think, that lambda CDM is not inconsistent with these observations. We cannot, of course, say that we have just added a cosmological test of lambda CDM because we don't know how well you would do if you had an alternate theory. You could start investigating alternative theories one by one, or you could cast about for phenomena that seem particularly difficult to grasp within lambda CDM. So I offer a possibility, the one that grabs me most at the moment. Here is the image of a nearby face-on spiral galaxy. Do you agree with me that astronomers have a special weapon in the pursuit of support for research? Admire this photograph. I wish the lights were a little darker and you could see the blue where stars are forming. Massive stars are hot and blue. Can you see the red? That's where ionizing radiation from those massive stars is producing plasma, radiating in the red line of hydrogen. You see a yellowish glow near the center. That glow extends over the whole area. That yellowish glow is the light of some several thousand million stars with masses similar to the sun. In our neighborhood, there are about as many planets as there are stars. It's a good bet that in this galaxy, there are some 1,000 million planets similar to the Earth's solar system. On those planets, wonderful things are happening that we, the human race, will never, ever see. Notice also the dust lanes that go into the center and, in fact, end at a star cluster with a relatively trivial mass of about 3 million solar masses. Dust settles to the plane. It's dissipative. The fact that you can trace these dust lanes all the way into a tiny star cluster in the center is telling you that most of these stars are in the plane with the dust and rotationally supported rather than zipping up and down out of the plane. Here's another example of such a galaxy. One does see atomic hydrogen, whoops, H1, rising above the plane, probably thrown out by supernovae. But it looks like the stars. It's a whirlpool, all the way in close to the center. There are stars outside the disk in some of these flat galaxies. You can see perhaps pretty well, yes, that there is this plume of light, presumably stars, outside of this galaxy. I'm not sure whether this is a technically thin galaxy or not, but it is pretty flat. And there are streams around the Milky Way too. You see it much better in this. Well, maybe you don't. This is supposed to be overexposed and show it. But anyway, you see it. But the important point, these plumes have a few percent of the luminosity of the galaxy. These thin disk galaxies are remarkably like simple whirlpools all the way into the center. There is progress in modeling the formation of such galaxies. Here's an excellent example, very impressive. But I draw your attention to the point, the point that there is the statistic J, the angular momentum of a star at a given position, and JC, the angular momentum it would have if we were moving in a circle at the position it is now. In this model galaxy, the distribution of J over JC is seen here. The spike at 1 simply means that lots of stars are moving in circular orbits or very close to it. The spike at 0 means that there are lots of stars also that are not rotationally supported. Instead, they're moving in the manner of the stars in an elliptical galaxy. They're moving in random directions. Forward, prograde and retrograde, radial, a mix. This is characteristic of a galaxy with a classical bulge, like M31, a bulge that looks a lot like an elliptical galaxy. It does not look like the Milky Way, where measurements show that the stars near the center are rotating on cylinders. The Milky Way is one of these thin disk galaxies, and it is a whirlpool right down close to that million solar mass black hole in the center. It's a real challenge making such galaxies. This is an example taken from the Aquarius pure dark matter simulation. I stress pure dark matter, baryonic physics can complicate the situation, but let us look at this for a minute. In the bottom plot made by G. Wang for us, only the dark matter particles that are within the nominal virial equilibrium radius at the present time are plotted. There are lots of particles out here. They're not plotted at any redshift. The particles that are within 3 kiloparsecs of the center, that's well within our radius in our galaxy, are labeled yellow, and they're plotted as yellow everywhere. The particles between 3 and 7 kpc are labeled black, and they're plotted black everywhere. Our position in our galaxy is just outside the black ring. Now you notice something very impressive, and a reason why people are always talking about merging in the lambda CDM cosmology. The dark matter particles that were near the center now were scattered all over the place at redshifts between 1 and 3. This is 800 kpc, by the way, a large scale. The star formation rate is known to have reached its maximum between 1 and 3. Where were those stars formed? Surely in the dense regions. They're scattered about. Where would these stars end up? They can't end up in a thin disk because they're plunging in, and stars move without dissipation. In order to make that thin disk galaxy, you had to have gas settle to the disk and then form stars. What in the world are you doing with the stars that formed at higher redshifts in these dense regions, and that no matter how complicated the baryonic physics, surely will not have ended up in a disk? Here is then the coda. Lambda CDM indicates considerable merging of dark matter clumps at redshifts between 1 and 3. That merging may be complicated by baryonic physics, but I don't see how you're going to avoid it. At 1 to 3 in redshift, star formation was rapid. That's observed. Where would these stars have formed? Surely in the clumps. Am I wrong? Where else could they form? Elliptical galaxies are known to be natural products of this merging of starry clumps, which is a good thing, a success for lambda CDM. But what do you do about these thin disk galaxies? They are common in our neighborhood. The astronomer John Cormandy assures me that of the nearest 20 large galaxies, 10 are thin disk galaxies. They have to have grown by accretion of clumps that contain very few stars, because the stars would end up in classical bulges or stellar halos. A real challenge, I think. How then could the rapid star formation at redshifts 1 to 3 have been confined to the clumps that were going to merge to form ellipticals and avoid the clumps that were going to form spirals? Would you agree that that's a real challenge? It seems so to me. So I come to my conclusions. As I've just described, the case for a lambda CDM-based galaxy formation theory is mixed. It has notable successes. It has, I think, some notable challenges, as in these thin disk galaxies. I am not suggesting you understand that lambda CDM is falsified. Like any theory, it's an approximation, successful in some limits, but to be amplified, to be improved in other ranges of scale. I am totally obsessed with the thought that the dark sector is at best a default. It works, so stick with it until it doesn't work, but surely the dark sector is more interesting than the lambda CDM model. Inflation. I have very little to say about it, but I would draw your attention to an interesting parallel between the situation in inflation now and the situation in cosmology in the 1930s. In each case, you have elegant ideas. In the 30s, general relativity theory, beautiful theory, and it has withstood the test of time. Inflation has elegant ideas too. In the 1930s, one had a very impressive redshift magnitude relation that fit the notion of a homogeneous expanding universe. In inflation, one has a near-scale invariant universe, and it is impressive to notice, not quite scale invariance, but rather tilting in the natural direction. In the 1930s, the cosmology of low redshift had a long way to go. But indeed, although no one, certainly in my generation, imagined it would be anywhere the way it is, it went a long way. And perhaps we will see the same in inflation. But I return finally to the thought line. I would conclude that the case for lambda CDM, redshifts less than 10, is about as good as it gets in natural science. I don't mean it's the final story. I don't think there are final stories in science. We just do the best we can. But I must say, you will perhaps only understand this if you are of my generation or better or similar. Perhaps you will not emotionally understand just how amazed I am at that state. Thank you.
Thank you very much, Jim, for your exciting talk. I'm sure there are many questions. Yes, please.
Jim, I'm puzzled by your worry about the thin disks. If I remember right, 30 or 40 years ago, you and Jerry Osterreicher wrote a paper which said that if there's a spherical distribution of what at the time wasn't known to be dark matter, that you'd get thin disks.
The direction is a little different. Yes, we celebrate thin disks as evidence for dark matter. Wonderful. But how did you make that thin disk? I am arguing that within lambda CDM, that is a real serious challenge.
More questions? Yes, please.
Okay, my name is Theo Nieuwenhuizen from Amsterdam. I would like to seek the problem closer to home. There is this moonstone which was taken by the Apollo mission, and now it has been found out that there's a lot of water inside. And that brings a problem for the formation of the moon, because obviously it was very wet when it was young. I have an explanation for that, but do you have one?
I do not.
Questions? No other questions? Unbelievable. I have a question. You have a question? Please. Okay, no, okay.
He wants us to speed up.
If I may.
Please.
Okay, so we are talking about cosmology. We have a standard model. We have the lambda CDM model. And our colleagues of the particle physics have their own standard model of particles. What do you think? Do you think that at some point the two community will be somewhat unified in the physics?
Yes, yes, a charming thought. It must happen. If we don't blow ourselves up in one way or another, science will continue to develop. how it will develop, what directions it will take. But we, in the cosmology community and in the particle physics community, have a lot in common. Think of that remarkable result in a number of neutrino species. I don't care if it's 3.5 or 3.0. It's so close. Dazzlingly beautiful coincidence. And yet, we have that obscene lambda. We have, on the other hand, dark matter, and we have wonderful experiments going on. One of these days it will be detected. I hope that the first reaction isn't to say we have discovered what the dark matter is. You may have detected just one minor component. I hope you have only detected a component. I hope there is more than one, so things are more interesting. But we will learn more, certainly, about dark matter. It has to happen. And lambda, well,
how do you compute it?
How do we understand it? It's such a deep problem.
Okay. More questions? If not, I think we should all thank again these people for this splendid lecture. Wait a moment, there is an announcement.
Just a reminder for those of you who are staying here in Noordwijk, there's a bus that will pick you up at 7 o'clock at the main entrance of the building. Okay? Thank you.
And now we have
and tomorrow we start at 9, so be here before that.